My name is Dr. Shobbusha Chishen. I am the Dean Research and Development of GIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Hello dear students, welcome back to my class on Physics 2. It is the 7th class in a row I am taking. I thank you for all your cooperation, for all the past 6 classes that you have been showing your patience, hearing. And one of the beauty of this video lecture is that anytime you can enjoy, or you can have my video on, because I'm offering some of the most modern topic of physics, that is quantum physics 2 now. That is the starting point of your Physics 2 course. And last video lecture I have already given a touch that where it will be applied. It will be applied in the areas like quantum computation, right? Some more beautiful things are waiting. Well, this is included in your course. We'll discuss that. We'll study that in detail.
And actually learning these few quantum mechanics 2 classes, and particularly now I am teaching you operator algebra, various techniques you will learn. They have got tremendous application in the areas, some of the problems of quantum mechanics I will be doing in the application in the problem of the semiconductors, application in the study of nanomaterials. Everywhere it is needed, okay, it is applied. So I requested you, and thanks for all your cooperation, that to be patient, to be to continue to work with me, okay, I should say, during this discussion. Talking is, whatever you learn is physics, okay. So talking physics is basically talking with you, okay. So you work with me and let us talk physics in between, okay. So what I did, I make a this is myself, obviously. This is the 7th lecture in a row. Fundamentally, you should remember that every day, that is, I'll tell you every day, I'll remind you that this issue, that in a quantum mechanics class, we talk about something very special. 4 things can happen in nature. A matter be matter-like, collision, Newton has taught you that. Wave be wave-like, superposition, interference classes of you in first year. Wave can be matter-like, photonic theory, Compton effect, photoelectric effect, etc. But we follow the idea of de Broglie, that is the wave nature of a matter. Wave nature of a matter has been proved experimentally by Davison and Jammer, which is the superposition experiment of electron waves. So electron can show the wavy property. So in a quantum mechanics class, I do not discuss the wave-like material behavior of electron, because because you know it from classical physics. We focus on this green line in the, okay, electron is no more a matter, okay, it is not showing material property, it is showing the property of waves. Electron is, just don't get confused. Electron is a matter. Electron has its own mass, momentum, matter-like property. But quantum mechanics tells us, Schrödinger, the de Broglie hypothesis tells us, Davison-Germer experiment tells us, there would be experiment in nature where electron can show the property of wave, that is superposition. And that is all about Davison-Germer experiment. And if electron shows wave nature, that wave is a wave of probabilities. That is not like physical wave, like sound wave or light wave or AC signal. It's a wave of chances, wave of probabilities. Okay, and that so finally a variable parameter is the wave function psi, and its modulus square gives a chance of finding the object at a given point, with total probability is 1. And in a physics problem, in a quantum mechanics problem, suppose I have got a solitary electron moving around the nucleus, to me electron will be represented by a function psi. We'll be getting psi. Psi is a function of mathematics by solving a differential equation known as the Schrödinger equation. This is a general form of Schrödinger equation. Now, for our class, Schrödinger is taking a bit of rest now. Okay, we're doing something else. Okay, and so we actually rather focused on what else I can give us, what else I can do for us. Okay, what else I can do for us. Okay, so that is something. We are focusing in a quantum mechanics course. Okay, the wavy nature of the matter, and how this wavy nature of the matter as manifested by the function psi is going to help you. The entire mechanics, as I told you in the last few classes, that entire mechanics you can actually generate out of psi. To me, electron is a function psi. So from psi, if you interact with psi, these are all the psi's, all the moving electron. If you have to talk with psi, psi will respond all the physical information, all the information of motion, position, momentum, kinetic energy, potential energy, all the parameters of motion, which are together called dynamical variable, can be extracted from psi. So how do you get it from psi? You have to talk with psi. Psi can respond to your answer. How does it respond? With the language of operator. How do you talk with psi? For anything you do in quantum mechanics, any information of motion, anybody moving, I told you, if a car moves, if a bus moves, if a train moves, that is also a mechanics problem. If an electron moves, proton moves, that is also a mechanics problem. And to describe any mechanics problem, any motion, you need to measure some dynamical variable. That may be position at a given time, that may be momentum, kinetic energy, potential energy. All these things will together describe the motion. How do you get them classically? That you can see in the table, that is known to you. I don't have to tell you that, but how it changes quantum mechanically, that is the approach you have to have already discussed in your class. Every variable, for every variable there exists a quantum operator. X will become x cap, p will become p cap, t will become t cap, capital T, kinetic energy will become capital T cap, potential energy will become Vx cap, Hamiltonian will become H cap, okay, and any energy becomes E cap, and every operator comes up with a formula. I requested you to remember that position and time do not change, it becomes same x and t, and momentum is a derivative operator with respect to space, so momentum is minus h cut del L x. If you remember this two, you can get kinetic energy, because kinetic energy is half mv square, everybody knows it, so that is p square by 2m. If you remember the form, if you use the formula of p, that is minus h cut del by del x, then p square by 2m becomes like minus h cut square by 2m due to dx2. So ultimately this, what you are doing, these operators are basically, their job is to do some derivatives or multiplication. So potential energy is a function of x. X does not change, potential energy does not change. Hamiltonian plus is a summation of kinetic and potential energy. So if you know x and t does not change, and momentum is, there's a differentiation operator, next three will follow you. You can calculate kinetic energy, you can get potential energy, summation of them is Hamiltonian, okay, and total energy, any energy is IH cross del L, time dependent operator. After that, I told you how do you exploit psi to get this information. Answer is that if I have got a function, say psi is a sine function, psi maybe e to the power function, I can only measure if I satisfy an eigenvalue equation. What is an eigenvalue equation? If I say, suppose in the second case, my wave function is e to the power ikx. If an operator p acting on the function gives you back the function, which is doing it in this case, p psi 1 is equal to p psi, that is p e to the power ikx will give you e to the power function back, multiplied with the constant h cut k, then measurement is possible. H cut k is the measured value. And then this function e to the power ikx is an eigen function of the momentum operator. Similarly, for kinetic energy also, you can measure kinetic energy e to the power function, and also with sine function also you can measure kinetic energy. The logic is that the operator t will act on the function and give you back the function multiplied with the constant. There is a basic structure of eigenvalue equation. Then and only then you can measure, and the constant is the measured value, okay. So I discussed it, and after that the last day actually came, we got this idea that if I have got a number of functions, so function psi 1, psi 2, psi 3 up to psi n, and they are eigenfunction of a number of the same operator O, okay, like that, O psi 1, all of them are satisfying eigenvalue equation, then the linear combination of them will also satisfy the eigenvalue equation, which is called superposition principle. It is of tremendous importance in the area of quantum computation. You see, you can see there it tells us quantum computation. It was there in the previous video lecture also, that quantum mechanics tells, if according to quantum computation, if you compare with classical computation, 0 and 1 of quantum computation are two quantum mechanical states, maybe spin up and spin down state of the electron. Unlike to classical computation, apart from 0 and 1, where there is nothing beyond 0 and 1, here mixtures of 0 and 1 are also quantum mechanical state, okay. So just to remind you, it's a beautiful, superposition theorem has got tremendous application in our quantum computation, okay. You see current, if it moves clockwise, it gives maybe spin down current, okay, which will be 0 state. If it moves anti-clockwise, it will spin the directional magnetic field according to Balsa, but it will spin out. Now the mixture of them is also an allowed quantum mechanics, not just up and down, not just two spin states, you know, their mixed state is also an allowed state. 0 may be a quantum bit. Once 0 means down spin state may replicate a quantum bit, up spin state may replicate a quantum bit. They are mixtures under a magnetic field, okay, they will get a mixed state of them, that will also be an allowed state. As you can see in the right hand side picture, not just up and down, any rotation means of the spin state is a mixed state of them, okay, that is also an allowed state. And this is the basis of quantum computation, okay. The number of quantum bits are enormously high, okay. Okay, so now let us concentrate a bit on this superposition principle again. Now if you look at this equation, here I can write down this as a psi is equal to a1 psi 1, a2 psi 2, a3 psi 3 up to n psi n is equal to summation over I1 to n I psi. Ai is called coefficient of linear expansion, okay, okay. And we obtain Ai, as I left in the last class, I told you at the end, through another idea called orthogonality condition. Now the statement of orthogonality condition is like this much: if you have got two functions psi m and psi n, their orthogonality idea is this much. It is a conjugate of the first function and the second function. If the integrate over the entire space, okay, there is a mistake here, okay, it will be psi m star psi nx, okay, that star will not be there, okay, okay. So if you do the integration, for similar function you will get 1, for dissimilar function you will get 0, and the stars means conjugation of the function, okay. So So now I'll just illustrate this with an example in front of you. And after that, we'll apply orthogonality idea for some physical problem. You know, it's a very important idea. Time and again, when we'll be solving problem, we'll be utilizing it. So let me just do it with an example so that you realize it. Okay, you'll be realizing it with an example. Let me explain it with an example. Okay, it will be easier for you. Okay, this is the example. I consider them as sine and cos function, and let's see. I'll do it by hand directly. Please check it. Okay. So let me switch off my video, no more necessary. You please see how it goes on. I hope it is visible to you. You please see. So this is the essence of superposition principle. The individual function psi1, psi2, psi3, psi8 up to are eigenfunction of the operator O. All of them are satisfying eigenvalue equation with O. You can see if that is the story, okay, it is up to psi n. Okay, if that is the story, then their linear combination psi is also satisfying the eigenvalue equation. This will also satisfying an eigenvalue equation with the same function. Okay, that is the meaning of the superposition theorem. So I can write down this in this way. As I have written, this Ci is called coefficient of linear expansion. This is called coefficient of linear expansion. Okay. Now this Ci, as I mentioned, is obtained from orthogonality condition. Okay. This is obtained from orthogonality condition. So now the orthogonality condition, as I stated, is like this much. This is the orthogonality condition. If I have got two functions, one of them is psi mx and the other function is psi nx, their orthogonality condition, this is one function, this is another function. Okay, so I have, suppose I take conjugate of this psi m star, this function, this is called complex conjugate of psi mx. What is meant by complex conjugate? If I have got a complex number z, its complex conjugate is called z star. This is the complex conjugate of this function. Okay, a minus ib. So now we're considering a and b are real. So if I take a product of them, you see, you will get a square plus b square, which is nothing but, you see, if I take mod z, magnitude of the function is like a square plus b square. So mod z square is nothing but a square plus b square. If I take mod z square, so you get an idea here. These two are therefore equal. Z star is therefore equal to mod z square. So I keep it separately here. This idea will be written. It will be needed later on. This will be time and again will be utilized here in my class. So now the orthogonality relation is this much, that it is a integration of these two terms minus infinity to plus infinity psi m star psi nx dx. Now this will be 0 if two different functions are considered, and this will be 1 ideally if two similar functions are considered. Now let me explain it, as m means the conjugate of the first function. Let me explain with an example. Example is the sine and cos. Okay. So if I present you the example, you will realize it. This is the example. So now I consider, suppose one function is sine function and the other function is the cos function. So psi m star, the conjugate of the function will be a star, and you know sine function is a real function. Say sine 30 degree half. So half means ki sine 30 degree, suppose half. Half means ki half plus I0. So if I take a conjugate of that, if I take conjugate of this, that becomes half minus I0. So this has got no meaning. So sine function is a real function. So if I do the integration now, it would be like this much. Minus infinity to plus infinity. If you put the value of psi nx, it is a cos kx. And if I put the value of psi m star x, it is a star sine kx. Now A and A star, as I have shown you in the last page, Z and Z star is equal to mod Z square. So A and A star will make mod A square sin kx cos kx dx. Now you know from your old knowledge, if you have to do this integration, you have to bring in a half, make it 2 sin theta, sin 2 theta, you do it like this. Now, the great advantage of mathematics is that you don't have to take the trouble of integrating. You write down it is to be 0 because you are integrating two dissimilar function. M is not equal to n. So I will get 0. That is the beauty of mathematics. That beauty of mathematics is that you don't have to, you see, get solving and doing an integration is a mathematical pen. You don't have to take the pen if you know the integrate this idea of arithmetic condition. Two different function, sine and cos, on integration is giving you 0. Now this is true for any two arbitrary function. This is true for any two arbitrary function. For example, one function, suppose one function is suppose psi mx is sine and psi nx is only 1. So now if you, that means if you integrate only sine function under the limit minus infinity plus, this will also going to be 0 because they are also m and n are unequal. Two different functions I am considering. So two different functions we are considering. Similarly, you may choose another case. Suppose one function is maybe a cos x, or another one function is x and the other function is say a sin x or a cos x. So here also m is not equal to n. So if you now again integrate this minus 2 plus infinity psi m star psi x dx, again I will get 0 because m is not equal to x. So that you get a method here that if I only integrate sine cos x sin x, two different functions will always give me 0 for this type of limit minus 2 plus infinity 0 to infinity. On the contrary, if I took this huge mathematical advantage, when we are solving long problem, you will realize it. Now m equal to n means both of them are same. That is basically, if I look at this equation psi m star x, now m and n are now equal, psi nx dx minus 2 plus infinity. Now m equal to n means both of them are m. So here also I will be writing down a sin kx dx, and here I will write down this formula, a star sin kx minus 2 plus infinity. Now this will give me a star into a is basically mod a square minus 2 plus infinity sin square kx dx. And you realize it, if you have to do it, you have to bring in a half here, 2 sin square theta. This will become 1 minus cos 2 kx like this. So because of this 1, you'll never get a 0 result. So the result will be always non-zero. It can become 1 depending on the value of a. Ideally, it will be 1. So that is the beauty of arithmetic condition. In general, if you have got two different functions, you will get for this type of limit minus infinity to 0, 0 to infinity, twice 0 to infinity, you will get non-zero result. If the same function and its conjugates are there, or square of a function like sine square cos square, and if you've got two same function and two different function, you will always get a non-zero result. Okay, sorry, two different functions will give you 0 results. Say if I make a if I write down and make a summary, that minus infinity to plus infinity psi m star x psi nx dx. Now this is going to be 0, m not equal to n. Examples, suppose one function is another function is sine or cos function. Suppose one function is x, other function is sine or cos, like this much, or many more cases may arise. And another option is that suppose both of them are same. Okay, I will get from here, I will get 1 if m is equal to n. M equal to n means ki same, m equal to n means same function and its conjugate. Okay, suppose suppose psi mx is sine its conjugate is also sine. Like this. Suppose this is cos. This is also cos. So basically when you integrate, it will be like sine square cos square, it will be giving you non-zero. It's a huge mathematical advantage. Please believe me, it will help you a lot. Okay. Two different functions, only sine, only cos, x sine, sine cos. Suppose another option is that, as I told you, suppose one of them is sine. As I have shown you, another one is cos. Okay, two different function will give you zero. No, it's a huge mathematical advantage, and not two same function is conjugate will give you non-zero result, ideally one. Now, another most important issue is that suppose I write down orthogonality equation minus 2 plus infinity psi m star x psi n x dx. Now I consider m equal to n case. So m equal to n case means both of them are same function. So I can write down both of them like this way. And because m equal to n, right hand side should be 1. Now this is just like as I told you a few minutes back, z into z star gives you mod z square. So if psi into psi star will give you mod psi square. Now this will be 1. Now it's a beautiful equation. You see, I told you at the beginning of quantum mechanics courses, mod psi square is nothing but the probability of finding the particle. Mod psi square is nothing but the probability of finding the particle at a point x at n time t. Now, but what does this condition gives me? This equation is the total probability, and you know that is normalization condition. There has to be 1. So basically, you see our orthogonality condition is also following the or normalization condition is also following the orthogonality condition. So it is giving me the normalization condition. So same thing I told you at the first year days. Okay, that same relation is coming. That is the beauty of mathematics. Okay. So now we'll make an utilization of this idea of orthogonality condition in a problem. So let us solve a quick problem. Suppose I am giving a function. So one of the application of orthogonality idea. Suppose I have got a function psi1. This is a normalized wave function. Suppose this is a normalized wave function. Wave function means this is producing this equation mod psi 1 squared dx equal to 1, and psi2 is another normalized wave function. So it will also satisfy the equation mod psi 2 squared dx equal to 1. Suppose their linear combination is equal to c1 psi1 plus c2 psi2 is also a normalized wave function. This is also normalized wave function. So this is going to produce mod psi squared dx integrated from minus 2 plus infinity is equal to 1. So now the condition is that suppose one of the coefficient is given. Suppose you are given c1 equal to 1 by root 2. You have to get c2 value. What is the value of c2? So what I will be doing, I will be straightforward using this equation. Okay, I will replace psi with this expression. So I can write down psi in this formula. Mod psi star means psi star psi dx. So if it is psi, I can get psi star by this equation as c1 star psi 1 star plus c2 star psi 2 star. So my job is to replace psi 2 star here, psi star here, and replace psi here. If I do the replacement, the job will be done. So let me do it. So basically, if I do it, it will be like this much. Mod psi square dx equal to 1. Now this is, as I have written, this is nothing but the product of psi star psi dx. Psi star is nothing but c1 star psi 1 star plus c2 star psi 2 star, and psi is nothing but c1 psi 1 plus c2 psi 2 dx integrated over minus 2 plus infinity, right hand side is 1. Now if you do a little bit of mathematics, you'll get 4 terms here. This will be taken product. So minus 2 plus infinity C1 star C1, psi1 star psi1, C2 star C2. You see, this is nothing but C2 star C2, and these two, psi2 star psi2. Again, the product of this term and this term, first term and last term. This is C1 star C2, psi1 star psi2, and next term is the product of these two terms, C2 star C1, psi2 star psi1 dx. Right hand side is 1. Okay. So I can write down this equation in this way. You see, this can, the first term will be written as modulus of C1 square minus 2 plus infinity modulus of psi1 square dx. Now next term will be modulus of C2 square minus 2 plus infinity modulus of psi2 square dx. Now integration of this term will be 0 by orthogonality. Integration of this term will be 0 by orthogonality, and right hand side is 1. Now integration of this term is 1. This is also 1 by a normalization condition. So you get this much, mod psi1 C1 square 1 plus mod C2 square 1 equal to 1. C1 is given as 1 by 2, 1 by root 2. So mod C2 will be equal to 1 by root 2. So that is the value of mod C2. So you have got the values. So therefore, if I put the value of psi, so psi will be equal to C1 psi1 plus C2 psi2. If I put the value, this is 1 by root 2 psi1. And if I put the value of psi2, 1 by root 2 psi2. Now let me explain the meaning. Meaning is that, what does it mean? You see, the coefficient of this is like C1 psi1 plus C2 psi2. It's a superposed state, you know. I tell you the probability of occupying C1 state is, probability of occupying C1 state is given by mod C1 square, and probability that the particle should be in C2 state, psi2 state is given by, okay, mod psi2 square, sorry, mod C2 square, and C1 square is half, C2 square is also half. So total. Now if I choose a real life example, that is an example of hydrogen atom. Okay, for example, I choose a hydrogen atom, and suppose hydrogen atom, there is only one electron, and suppose the first core, these are the Bohr orbits. If the electron is in the first Bohr orbit, suppose its wave function is psi1, and if the electron is in the second Bohr orbit, suppose the wave function is psi2. Suppose I've got a container where there I've got 2 hydrogen atoms, or I've got, say, suppose 10 hydrogen atoms. Suppose electron may be in either of n equal to 1 or in n equal to 2. So the combined wave function is 1 by root 2 psi1 plus 1 by root 2 psi2, because psi1 is also an electronic wave function, psi2 is also an electronic wave function, but psi is a wave function of the electron in hydrogen atom case. So the probability, whether out, suppose I have got 10 atoms, so it's their probability that 5 of them, okay, that is 50% of them, okay, will be with psi1 state, and 50% of them will be in the psi2 state. 2 options are there. Okay. Now another one of this is one of the popular examples that often comes in examination that I have done in front of you. Okay. Another application of normalization condition is that much. Suppose I have been given a wave function, say between x equal to 0 to x equal to a. So this is a problem 2. My wave function is like a sine pi x by a, and elsewhere it is 0. So you find out, you use normalization condition to get a. So normalization condition is this much, minus 2 plus infinity 1. Suppose this is minus infinity to 0 is this side. Say let me call it region 1. 0 to a, let me call it region 2, and a to infinity, let me call it region 3. So if I divide the limit minus infinity to 0, mod psi square dx, region 1, 0 to a, mod psi square dx, region 2, a to infinity, mod psi square dx. Now this will be 0 by orthogonality condition, you know, because here it is by the description of the function, it is 0. Right hand side here also it will be 0 in region, this is region 1, size 0, region 2 also size 0. So I'll be happy with the region 3. So if I do it, it is like this much. If we put the value, it is mod a square 0 to a sine square pi x by a dx. Right hand side is 1. So if to do it, you have to bring in a half here. It will be 2 sine square theta. You have to write, make it 1 minus. Okay, it would be like 0 to a 1 minus of cos 2 pi x by a dx. Now this cos term will give you 0 by orthogonality condition. Sine term will give you a. So mod square by 2 into a equal to 1. So this will be giving you a equal to root over 2 by a. Root over 2 by a. So this is one of the popular problem of quantum mechanics. This is actually, this problem will come up. Okay, we'll solve it again as a problem later on. So this has been the two applications of orthogonality relationship. Let me get back to my PowerPoint presentation PPT again. You see, this is something I discussed just now. Okay, beautiful equations are there. These are the problems we solved just now. Okay, this is the problem just now we have solved. This is the problem. So our discussion with operator will be continuing. Next topic we'll introduce is operator algebra. So for today, I think it is thank you to you. We'll meet tomorrow again with the operator idea. Thank you.